So, in the last module we looked at multi-threading, and in this module we are going to discuss the need for multi-core processors, are also called as chip multiprocessors. So, there is a significant demand from the user side for high computational power. The applications such as image processing, speech, video, and several other applications are actually requiring high performance computation. So, in order to support these demands, we need to come up with efficient processors so that the processors will have necessary hardware components to process the different application requirements. So, in order to come up with high performance processors, we have a support from the VLSI process technology in terms of the number of transistors integrated on a chip. So, if you see here, over a period of time, the number of transistors integrated on a chip is tremendously increased. And now currently we are in a stage where we can integrate billions of transistors on a single chip. So, once we have billions of transistors in a single chip, so we can use these transistors to provide whatever the functionalities are required by the users, so that we can take care of their demands and provide high performance computation. So, we need to exploit these available transistors to provide various functionalities to satisfy user requirements, and also we can improve the overall performance of the processor. In addition to this, there are certain things which let us to go for multi-core processors. So, the superscalar processors, whatever we have discussed earlier, are corresponding to a single core of the systems. Even the multi-threading systems, whatever we considered, are also part of a single core systems. So, once we have a single core system, the amount of performance we get is not significantly increasing because of various reasons. So, one of the main contributors for the overall performance improvement for single core processors is the frequency scaling. But so the scaling up of frequency cannot go beyond a certain value, mainly because once we have billions of transistors clocking with the high frequency, then all these transistors are going to consume energy, and that translates to the heat, because once the amount of power increases, and the power per unit area is called as a power density, and the power density translates to heat, and once the power density increases, the amount of heat generated on the chip will be significantly higher, and as a result we will have thermal issues. So, in order to tackle these thermal issues, we should not increase the clock frequency significantly. So, this is called as the frequency wall. So, we cannot scale up the frequency beyond certain value, and if we scale up the frequency beyond that value, then we are going to have power and the thermal issues. So, as a result, we should not go for the frequency scaling up significantly. And the second, the driving force for us to go for multi-core system is the ILP wall. So, here we already discussed in the superscalar processors. So, if we go for the wide issue superscalar processor with a deeper pipeline and with aggressive superscalar techniques, we can improve the performance. So, when I say aggressive superscalar techniques, so the techniques such as the speculative issue of instructions and having support of advanced branch predictors and so on. Once we have deeper pipeline with the multi-issue the superscalar processor, we can have a significant number of in-flight instructions in our processor at various stages in the pipeline. And once we have many in-flight instructions, we can look at independent instructions among these in-flight instructions, and then we can schedule these independent instructions onto functional units, and as a result we can overlap the execution of instructions, which in turn improve the overall performance. But from this graph, if you can see, Here the x-axis shows the effort we put in and the y-axis shows the performance we get in return. So, started with the scalar in-order processor, moved to a moderate pipeline superscalar processor with out of order execution, and further moved to a very deep pipeline superscalar processor with out of order execution as well as aggressive superscalar mechanisms. If you see here, as we move from scalar in-order processor all the way up to very deep pipeline superscalar processor, the amount of effort we put in will be significantly increased. And also, in order to support this aggressive superscalar mechanisms, out of order execution and deeper pipelines, so our hardware also is going to take more area and other things. And once we have these extra components, and what is that we are going to get in return in terms of the performance. So, the performance improvement is not significant compared to the amount of effort we put in. So, we can go up to this point, but after that you can clearly see the performance curve is almost flattened. So, this indicates that we are going to get very little gain in terms of performance with a significant amount of effort we have to put in to extract the amount of instruction level parallelism available in applications. So, that is called as ILP wall. So, applications are not having a significant instruction level parallelism. As a result, whatever the effort we put in to extract the available ILP, the amount of returns we are going to get is very small, and as a result we have to look for some other alternative. And the third driving force for us to go from single core to a multi-core is the power density. So, as I mentioned earlier, power per unit area is called as a power density, and once we have more and more transistors integrated on a single chip, and that too the area of the chip is very small, and once we are clocking all the available transistors in the chip with high clock frequency, these transistors are going to consume power, and as a result the overall power density is going to increase significantly. And because of that, our power density is very high, and this power density translates to heat, and so if you are not going to take care of this, then the chip may burn out, or otherwise like it is going to give undesirable results when we use that for some computation. So, this is called as the power wall. And finally, the last one, but it is a very important one, this is the memory wall. This says that the performance gap between the processor and the memory is widening over a period of time. In other words, the processor performance is improving year by year significantly, but the memory technology is not developing significantly. As a result, the memory performance improvement rate is not as high as that of the processor performance rate, and because of that we can clearly see here there is a significant gap between the processor performance and the memory performance. So, once we are executing an application on a processor which is working with high frequency, and when it wants the data, the memory is the one which is going to supply the data. So, if the memory is not supplying the data as and when required by the processor, then the overall computation will be stalled, and as a result the overall performance of the system will be degraded. So, in order to tackle this memory wall problem, we already discussed in one of the previous modules about the multi-level cache hierarchy. So, we need to break all these walls. So, in order to break these walls, that is ILP wall, frequency wall, memory wall, and the power wall, so we have to come up with different designs. So, that means we need to think of a paradigm shift in our processor designs. So, rather than getting the work done by using a bullock, what we can do is we can get the same thing done by a collection of the dogs. This shows that rather than considering a complex superscalar processor with aggressive superscalar techniques and deeper pipelines to get our computation done quickly, we can actually consider a collection of simple cores but all these cores are working in parallel, so that our computation can be finished quickly, and also we can reduce our overall power consumption, and the design complexity also can be minimized, and as a result the overall performance improved at the same time without increasing the amount of power consumed for the computation. So, in other words, if we have a superscalar processor with a deeper pipeline with an aggressive superscalar mechanisms, let us assume that this processor is going to take 1 unit of area and it is going to consume 1 unit of power, but it is going to give you 1 unit of performance. Now, rather than considering this complex superscalar processor which may be working with x gigahertz clock frequency, now we scale down the clock frequency of our new processor, and also we consider a simple processor, and assume that this is a simple superscalar processor or even a simple in-order processor, and which is actually working with much lower clock frequency as compared to this one. And because this is working with lower clock frequency and also it is not having any aggressive superscalar mechanisms, so as a result the performance may not be as that of the performance whatever we get with this complex processor, and because we are running this with lower clock frequency, the power consumption will be significantly reduced as compared to the power consumption for this complex core, and also because of this simplicity in design. So, this is also actually taking a less amount of area. That may be because like we do not have to consider our dynamic scheduling mechanisms, we do not have to consider aggressive the superscalar mechanisms such as advanced branch predictors, deeper pipelines and so on. So, as a result we may reduce the overall area occupied by this processor. And once we reduce the clock frequency, we know that the power consumption is proportional to C V square F, where F is the clock frequency, V is the supply voltage and C is the capacitance. So, once we clock down our frequency, we have to reduce our voltage also. So, once we reduce the voltage, then because this power consumption is quadratically dependent on the voltage, so power consumption will be significantly reduced because of scaling down our voltage, and as a result we consume a very little power consumption as compared to the power consumed by this bigger one. So, assume that this power consumption is 1/4 of whatever the power we consumed here, and the performance is maybe somewhere around 40% of this particular thing, and the area occupied by this processor you can assume it is a 1/4. So, now we have this much area dedicated for our chip, but because of our revised design, a simplified design, we are consuming only 1/4 of the area. Now, what we can do is we replicate the simple core 4 times. So, as a result, now we are actually taking the same amount of area as that of this complex core, and since this is consuming 1/4 of the total power consumption whatever consumed by this complex core, and when we replicated this 4 times, so we can clearly see here our power consumption is almost same as this, but the performance is improved as compared to this. So, this actually gives us a motivation to go for a multi-core systems rather than considering a single core system. Here we have collection of simple cores, and all these cores are working simultaneously to compute our required task, and if the task is highly parallelizable, then we can divide our task into 4 subtasks, and each of these subtasks can be executed on each of these simple cores. So, effectively our overall throughput will be improved. In other words, the overall performance is going to be improved when we consider a multi-core system, and so as a result, rather than considering a faster or a powerful processor, consider a collection of simple and the slower cores, and once we have this collection of simple and slower cores, we can execute our parallelized application so that the overall performance can be improved. So, this is the overall idea behind going from a single core processor to a multi-core processor. So, what is a multi-core processor? If you see a single core system, so we have set of registers called as a register file, we have functional units, we have the interconnection network connecting different components, like register file is connected to the external components by using this bus interface, and there is an interconnection here, and also there is an interconnection between this register file to this ALU or the functional units, and similarly there is an IO input output bridge and which is connected to the main memory. And also we have not shown here, but we can consider like multiple levels of cache hierarchy within this, and also there will be several other components connected to this IO bus, such as disk controllers, graphics adapters, USB controllers, and so on. So, this entire thing corresponds to a single core system. So, here this part is called as a core, and the rest of the things are the other components associated with this core to make this into a full-fledged system. Now, in a multi-core processor, we just replicate this component multiple times. We can see here this is a bus interface, and currently this bus interface is connected to this single set of register file and the functional units, and also not shown, but also we have the cache memory and other things. Now, we replicate each of these things into multiple numbers. So, here we have 4 core system where all these 4 cores are connected to this bus interface, and this bus interface is in turn connected to the other components of the system, and these other components are shared by all the cores of this particular system. So, here this is called as a single core system, and whereas here this is a 4 core system. So, the only difference between the single core and the 4 core is here we will have 4 single cores replicated, and rest of the other things are the same. So, once we have this multi-core system, now because each of this core can work independently and they can share all other resources similar to the they can share all other resources with all other the cores. So, as a result, so once we have this multi-core system where each of this core can work independently and they can share, and each of this, so now once we have this multi-core system, each of these cores can work independently and all these cores share all these resources. And once such system is there, now we can actually execute independent applications or multiple threads of a same application on all these cores simultaneously, so that we can improve the overall throughput of the system, which in turn improve the performance of the system. So, example multi-core processors are one is like Core i7 processor from Intel and Power 7 processor from IBM. Here we can see Core i7 processor which has 4 cores, and each of these core has all the support for executing instructions in out of order fashion, and also it has multi levels of caches, L1, L2 caches private to each of these cores, and there is a shared cache, and this cache is shared by all these 4 cores. And also in order to handle the graphics related things, this processor also has a separate component, the processor graphics, which takes care of processing all the graphic applications, and also this extra components which are actually having a support for memory controllers and also connecting to the other components of the system. So, this whole thing corresponds to a Core i7 processor from Intel. And similarly, when we consider IBM the Power 7 processor, we can clearly see here we have 8 cores associated with this, and the L3 cache is there, and each of the core has internally private L1 and L2, and also the support for memory controllers and support for connecting to the other resources in it. So, in other words, these examples show that multiple cores can be integrated on a single chip, and because the cores are now placed on a single chip, so the communication between core to core is not going to take a significant amount of time as compared to a multi-processor system where multiple processors are physically apart, and these systems are connected through external communication links and so on. So, as a result, these multi-core processors are going to improve the overall performance of the system. So, once we have these multi-core processors, now the question is whether we have to consider all the cores similar in type, or do we have to consider a different collection of cores in our multi-core system. According to Amdahl's law, if alpha is the fraction of the code that can be executed parallelly, then the speed up what we can achieve with n number of processors is 1 by 1 minus alpha plus alpha by n, where n is the number of processors. So, if alpha is, let us say, 95%, so that means when you have 95% of your code can be parallelizable, and even when you consider 64K, 64 into 1024, that is 65,536 processors to execute your computation, we can clearly see here we can get around 20x speed up in our system. So, that indicates that the amount of speed up we can achieve is limited by the fraction of the code that can be parallelizable. Even when we have 95% of the code that is parallelizable, because of this 5% sequential code in the program, we are not gaining a significant speed up in our system, even when we consider 65,536 cores. So, that shows that it is not always good idea to consider uniform cores in our multi-core system. We can actually go for heterogeneous multi-core system. When we consider all the cores in our system same, then that is called as a homogeneous multi-core system. But when we have some cores different from the other cores, then we can say this is a heterogeneous multi-core system. An example for heterogeneous multi-core system is IBM Cell. So, here we can clearly see we have one complex core or a processor and a collection of simpler cores, and when there is an application which is highly sequential in nature, then we can use this complex processor or a powerful processor to execute the sequential portion. But whereas if we have a highly parallel application, we can execute that parallel portion on this collection of simple cores, so that we can improve the overall performance. On the other hand, if you see a homogeneous multi-core system, this is from Intel. So, here we have 4 cores, and so here all the cores are similar in nature in terms of the superscalar techniques, in terms of the amount of cache associated with each of the cores, in terms of the clock frequency with which each of the cores can work. So, all these are similar. So, as a result, this is called as a homogeneous core. But again, depending on the type of applications, we have to consider whether we have to go for homogeneous multi-core or heterogeneous multi-core processors. So, these are the examples of the current day multi-core processors from different vendors, processors from Intel, processor from AMD, processors from Tylera, and so on. So, there are different type of the multi-core processors available in the market, and each of these have different characteristics and different computational powers and the different number of cores inside it. And so, in summary, we are in the multi-core era where rather than looking at scaling up the clock frequency we are now looking at scaling up the number of cores in the processor. We need multi-core processors because these multi-core processors are going to address our different wall problems, the ILP wall problem, power wall problem, frequency wall problem, and so on. So, the first thing is to address the frequency and the power limits whatever we faced with the single core processors in order to improve the performance. So, we can consider multiple slower cores rather than a single complex core, and we can scale the performance by increasing the number of cores rather than scaling up the frequency, and depending on the type of applications we can go for heterogeneous cores. And to address the instruction level parallelism limits whatever we faced with the single core processors, because once we have multiple cores in our multi-core system, we can execute multiple threads on each of these individual cores. We can exploit coarse grained parallelism to improve the overall performance. And finally, once we have multiple cores and still we have the memory wall problem, in order to address this memory wall problem, we have to go for the deep distributed cache hierarchies. These cache hierarchies are distributed across the multiple cores in our multi-core system, but these caches can be shared. So, effectively we can consider shared distributed cache across all the cores, and also we can consider multi levels of the cache hierarchy. So, rather than one level or two levels, we can consider 3 levels. Even there are the current designs targeting at 4 level cache hierarchy. So, once we have a deeper cache hierarchies, so we can minimize the number of times going to the memory to get the requested data. So, we can keep the requested data in our multi levels of cache hierarchy, where typically first 1 or 2 levels can be considered as private caches for each of the cores, and the remaining levels of the cache hierarchy can be considered as shared across all the cores. And with that I am concluding this module, and in the next module I am going to discuss the issues that are associated with this multi-core processors and how to take care of those issues, so that we can use multi-core processors without any problem and we can improve the overall performance of the system. Thank you.